So this brings us to the ideal gas law. All of those simple gas laws, and there's one more called Gay-Lussac's law, can be combined into a single law that incorporates all of them. And we call that the ideal gas law, and it's PV equals nRT. It's another one you need to know. That's probably the most important one, because from that, I'll show you how you can get all the other gas laws. So here's our familiar pressure, volume, amount of gas in moles, temperature in Kelvin, and then we've got a new one, R. R is the ideal gas constant. And the value of it that we're going to use is this, R equals 0.08206. Liter atmospheres per mole Kelvin. Those are crazy units. R can have a different numerical value if the units are different. Okay, but we're just going to use this one. If you are interested in how all of these get incorporated into the ideal gas law, I would love to talk to you about it, but I'm not going to do it in lecture. The one thing I do want to show you is how to get any gas law you need out of the ideal gas law. So the ideal gas law is PV equals nRT. So that is true for any sample of a gas, right? So if we took another gas, that's a blue gas, we'll take a green gas. It is also true that PV equals nRT for that gas. The pressure is different, the volume is different, N is different, the temperature may be different, but the relationship is the same, okay? If I take this equation and divide both sides by an equal amount, it's still an equality, right? It's still equal. So what if I divide this side by green PV and I divide this side by green nRT? PV is equal to nRT, so I'm dividing both sides of this blue equation by the same amount. So it's still equal, right? Well, colors are great on PowerPoint, but they don't work so great writing on paper. So let's give these some subscripts. I'm going to call this 1, blue is going to be 1, and green is going to be 2. I'm not going to put numbers on R because R doesn't change. So the R's cancel out. R divided by R is 1. So I'm just going to completely get rid of him. So there I have a relationship between all 4 variables. You probably won't run into a question that has 4 variables changing, but you might see one that has 3. So let's derive one of the gas laws. So pick Charles' law or Avogadro's law. Which one? Charles' law. So Charles' law has volume and temperature. So with Charles' law, volume and temperature are changing, but the pressure and the amount of gas are not changing. So for a Charles' law problem, pressure 1 is equal to pressure 2. So, So those would cancel out. And the amount of gas isn't changing. The number of moles that you start with is the number that you end up with. So those would cancel out. Okay with that? It didn't change. It's the same. Okay, so since I can, I'm just going to erase those. So what I have there is just a rearranged form of Charles' law. If I take this value and put it in the numerator on that side, take this value, put it in the denominator on that side, I end up with V1 over T1 equals V2 over T2. There's no magic in getting this particular formula or arrangement of it. I could take this one and use it in my problem. Well, let's say I needed to solve for T1. Well, I could just rearrange this, solve for T1, and go on my way. So you can derive any of those equations by taking one ideal gas law, dividing by the other. Any questions? Saves a lot of memorizing. Let's do an ideal gas problem. An 8.50 liter tire contains 0.552 moles of gas at a temperature of 305 Kelvin. What is the pressure in atmospheres and psi of the gas in the tire? We have this title up here telling us this is an ideal gas law problem. I don't put titles like that on exams. How can you recognize what kind of an equation you need to solve the problem? Well, yeah, we've got three different variables here, so obviously it's not one of the simple gas laws. The other thing that you might recognize is there's nothing that's changing. They're not saying it was heated or it was compressed or we added. There's one volume, there's one N, there's one temperature, we're asked for pressure. So that's all four of the variables. You could also just set up a table and start filling it in. What you'll find is that you only have one row. There is no second set of stuff. And so then you see, well, I have no ones and twos, it must be the ideal gas law. And this is an ideal gas law problem. So let's organize this. 8.50 liters. Yeah. Okay. Let me get a pen here. So 8.50 liters. They don't say what that is, but the unit liter tells us that's the volume. And then it contains 0.552 moles. And we should recognize, okay, moles, that means that's the amount of gas in moles. And then temperature is 305 Kelvin. Isn't that nice? They didn't give us degrees Celsius. So I need PV equals nRT. Some students call that PIV-NERT. PV equals nRT. What am I solving for? Pressure. So divide by volume on both sides. Pressure equals nRT over V. So what's N? Well, we've got it labeled right there, 0.552 moles. R is not in the problem. I encourage you to memorize this. It'll save you a lot of time. 0.8206 liter atmospheres per mole Kelvin. The units on R tell you what the units on your other variables have to be. So this tells me that my volume has to be in liters, amount of gas in moles, pressure in atmospheres, temperature in Kelvin. I've got liters, moles, and Kelvin. Things are good. So then we put R in here, 0.08206. I know it's tedious. Write out all the units. And then the temperature, 305 Kelvin. And all that is divided by the volume, 8.50 liters. Check the units. Moles cancel moles, liters cancel liters, Kelvin cancels Kelvin. I've got atmospheres left. Cool. 0.552 times 0.08206 times 305 divided by 8.5. How many sig figs? 3. So there's 3 sig figs, 2 extra digits. Unit is atmospheres. Bless you. So that's one of our answers, 1.63 atmospheres. But this question asks for 2 things. It also asks for the pressure in PSI. So you would have to go look up the conversion factor between atmospheres and PSI. If it was an exam question, I would give you that table. So you look it up and you find that PSI is 14.7 for 1 atmosphere. So I'm going to multiply my atmosphere pressure by 14.7. I'm going to get 23.892 PSI. And then I round that 23.9 PSI. 2 answers. Any questions? Let's do another one. What volume does 0.556 moles of gas occupy at a pressure of 715 millimeters of mercury and a temperature of 58 degrees Celsius? I have N, I have P, I have T. They're asking for V. There's nothing changing. This is ideal gas law. So 0.556 moles, well, that's N. And pressure, 715 millimeters of mercury. And temperature, 58 degrees Celsius. Bless you. PV equals nRT. We're looking for volume this time. Divide by P on both sides. Volume equals nRT over P. So I'm going to need R. Might as well write this down too. R equals 0.08206 liter atmospheres per mole Kelvin. These units are important. So this is in moles, that's fine. Millimeters of mercury is not going to cancel with atmospheres. I need to convert my temperature. Don't convert R, convert the individual ones. So I need to convert this pressure to atmospheres. This is a conversion you should know. 1 atmosphere is exactly equal to 760 millimeters of mercury. So converting that is not going to affect the number of significant figures. So I've got 715 divided by 760. My pressure in atmospheres has 3 sig figs, but I don't want rounding errors, so I'm going to keep 2 extra ones. Pressure in atmospheres. The Celsius temperature has to be converted to Kelvin. So 58 plus 273.15, 331.15. Kelvin. This was measured to the nearest 1 degree, and so my converted temperature will have uncertainty in that one's place. Now I have all the numbers I need. I can plug them into the equation. So the volume equals N, 0.556 moles, times R, 0.08206 liters, atmospheres per mole, Kelvin, times the temperature, 331.15 Kelvin, and then divide that whole big old mess by the pressure, 0.94079 atmospheres. Let's make sure the units cancel. Here I've got moles and moles, and I've got atmospheres and atmospheres, and Kelvin and Kelvin. So I'm going to do the math, 0.556 times 0.08206 times 331.15 divided by 0.94079. How many sig figs will this answer have? 3. So there's 3. Write down 2 more. I'm going to write down 3 more because I don't feel like rounding all that up. It's okay. It's 597, and that would round to 60, but that's, I don't know, I just don't feel like doing it. Whoops. Why am I writing atmospheres? What's the unit? Liters. Okay, so now I'm going to round. It's going to be 16.1 liters. Why isn't it 2 sig figs? Because of the 58? Because when we convert 58 degrees into Kelvin, we gained a significant figure. Because rules of addition say that you go to the number of decimal places. Yeah. Any other questions?